Good morning, everyone. How's it going today? Today, we're going to be talking about the FineWeb dataset. Now, this is a project by Hugging Face, and it is a great example of how to gather all the data that you need to train a large language model. This actually is also available in the form of a very nice blog post, and it is very educational. If you want to read more about it after watching this video, feel free to read this post. It is very, very well made, and there's a lot of very useful information, and there's, of course, a paper as well. Now, this one right here dates from a couple of years ago, but the information is still pretty relevant, and it teaches you a lot about how large language models nowadays are made. The slides of this are also in the description in case you want to give a talk about this later on. So without any further ado, let's actually get right into it. Okay, so first of all, why would we talk about the FineWeb dataset anyways? Why is this relevant? And the reason for this is that there is very little information on the web about how to create data sets to train these large language models. Precisely because even if a company that creates large language models publishes these models open source, they rarely publish their pre-training data as well, because there's just very little incentive to do that. So we set out to create an open data set that is very good and that trains very good large language models. And we documented pretty much every single step of the process of creating this to show you how you can do this yourself. And what we're going to be talking is mainly two flavors of this data set, which is, first of all, the FineWeb, which is the regular FineWeb dataset, which is a 15 trillion token dataset in English derived from common crawl dumps. And we're going to be talking about every single step that we took to create this dataset right here. And after that, we're going to talk very quickly also about the FineWeb-Edu dataset, which is more distilled version of the FineWeb dataset, in which we used some open models to extract only the most valuable and educational data from this dataset and ended up with a 1.3 trillion token dataset that actually performs even better than this 15 trillion token dataset. So yeah, we're going to be talking about both of them. The core idea behind the FineWeb is similar to decantation. So we are going to be starting with a very large corpus of text, which comes from the common crawl dumps, which is just a lot of raw web data. And then we just going to apply a series of transformations and a series of cleaning steps to make it a refined FineWeb dataset. And then on top of that, we're going to refine it even more to get to the FineWeb-Edu dataset. All right, so let's start off with the first part, which is actually getting the data from the web. You probably have heard that large language models are trained on a huge corpus of data that comes from the entire web. Now, how do you do that? There are, of course, multiple ways, and different companies do this differently. Some, for example, like OpenAI or Anthropic, they crawl the web and scrape the web themselves to get their own extracts of the web. What we do, or what we did right here, is we actually took the snapshots from Common Crawl. Now, Common Crawl is an open nonprofit organization that publishes snapshots of the entire web every 1 or 2 months, and they have been doing that for years. So the starting point for this dataset is precisely these snapshots from Common Crawl. So we started with 96 snapshots released since 2013, and each snapshot contains hundreds of terabytes of raw HTML data. Now, as you can imagine, there is going to be a lot of data in here, and a lot of it is going to be very dirty. In other words, there is going to be a lot of code or a lot of contents in this data that is going to be basically just boilerplate, spam, navigation menus, duplicated pages, or also non-English text. So what we did is we extracted that data and tried to clean it. And there are basically two approaches to do this. What Common Crawl actually does is that it allows you to download these extracts or these snapshots of the web into different formats. One is WARC files, which stands for Web Archive Files, which is the raw HTML data. It is, of course, more expensive to process because you have to clean it yourself. Or they also offer a type of files that are already extracted. So there is supposedly no HTML in there. So it's only text-only files extracted by Common Crawl themselves. It is, of course, cheaper and simpler to process. But in our tests, we figured that training tiny models on this dataset actually performed worse than on this dataset plus our own cleaning methods. So what we did is we downloaded the raw HTML and metadata files, and we used Trafalgadura to extract the text from these. And just for the record, this is probably the most expensive part of the entire process. So for smaller teams who are trying to do something like this spot right here might be one that they can skip. Although we did find that, as you can see right here, when training a tiny model on this dataset and another one with the same architecture on this dataset right here, we ended up getting much better results with our own cleaned up version. So that was the first step. All right, so how do we approach the cleaning and filtering of this huge corpus of already extracted data? Ideally, we already have this huge data sets, huge snapshots that are not in raw HTML, but in nice, beautiful text, but we still have to clean and remove content that we do not want to train our models on. And in order to do that, we did some very standard base filtering. First of all, we removed adult content using a URL block list. We also removed all of the data in this dataset that is not in English. There is, by the way, a second version of this same dataset, which is multilingual. I will leave a link in the description to that one as well. But in this particular one, we're dealing with only English data. And then we just added some extra quality filters for repetition to make sure that we do not have too much repeated data. The result after the whole thing was that we ended up with about 36 trillion tokens. This is just the first step of filtering. And now we're getting to the more tricky part of the process, which is deduplication. Now, the web is, of course, full of repeated content. There are mirrors, there are scraped copies, there are templates, there are syndicated articles, there are recrawled pages, and all of that just makes for a lot of repeated content in our dataset. So we had to deduplicate. Why? Well, deduplication is a process that many teams use very often because it improves model generalization, it reduces memorization of your model, and also, very importantly, you avoid wasting training steps on repeated text, which means that you don't end up spending extra resources retraining your model on text that it has already seen, and basically just increases data diversity. So we used MinHash to deduplicate this huge corpus of text against itself. And the first approach that we took was actually a failed one because we assumed that more deduplication was better. So what we did is first we deduplicated the entire dataset against itself. And the way to do this is remember that we have about 96 snapshots of the web that we got from Common Crawl. And what we did is, first of all, we took the first snapshot, or the most recent one, and we deduplicated it against itself. Then we went to the previous one, and we deduplicated that one against the newer one that was already deduplicated. Then this new deduplicated crawl, we used it to deduplicate against the older one, and then again the older one, and again the older one, all the way until the last one. And by the oldest crawls, since they, of course, are being deduplicated against the entire set of text from the previous Common Crawl extracts, this process was removing about 90% of the data from the oldest ones, which of course can be either very good or very bad, but we ended up with 4 trillion tokens instead of the 36 trillion tokens that we started off with. And that wouldn't be too much of a problem if the quality improved, but it did not. So when we trained a small model on both the deduplicated dataset and the non-deduplicated dataset, we found out that actually the results were pretty much the same. So we did not improve at all on our performance. We certainly did not get closer to our standard that we set out to achieve, which is the refined web dataset. Now, if you're not familiar with the refined web dataset, it is the dataset that is open, and it was used to train the Falcon model. So what happened here? Why did global deduplication actually not work? We figured that we in the end ended up removing very valuable data from all of these older snapshots. And in order to figure out, we took one of the older snapshots of this data set, and we trained a small model on the portion of the data that was removed, and then another one with the same architecture on the portion of the data that remained. And we figured and we found out that the model that was trained on the removed data actually performed better than the model that was trained on the data that was kept in this very old snapshot. So basically, what that meant is that we were removing very valuable data from our older snapshots by this very aggressive deduplication. And upon closer inspection, we actually found out that the data that remained after all of this was basically just template data, navigation data, ads, and stuff like that. So this was definitely not the way to go. So we changed the approach, and we used the duplication within each dump, and then we just added all those dumps together. So for the latest dump, we deduplicated it against itself. Then the previous one, we deduplicated it only against itself, not against the newer one. And every single one, we just deduplicated it within itself. We kept the text. And then by the end, we have this nicer FineWeb dataset with about 15 trillion tokens. And this actually ended up performing much, much better. So now we have this FineWeb dataset with independent min hash, which finally reaches the same performance as the refined web dataset. And as you can see, here are our previous attempts, and we are performing much, much better now. And just for the record, in case this is not clear, what these plots are measuring is the aggregate score of tiny models that we train with the same architecture and same design on these different datasets. And then we just evaluate these models among different benchmarks, such as NMLU. And then we aggregate the score on all of those benchmarks, and then we plot that right here. That is how we measure how good a data set is. And we finally got to the point where we have a data set that is comparable to the refined web data set. So pretty good. After this, we added some additional qualitative filtering. So we compared our FineWeb dataset towards a very strong baseline, which is the C4 dataset. Now, the C4 dataset is a very well-performing dataset that is actually very impressive because it achieves incredible results by just applying 4 very strict rules to its dataset and just removing every text or every piece of data that does not pass these rules. So first of all, it removes documents with bad length profiles, or essentially documents that do not end in a punctuation mark. So if you have a document in your dataset for which the phrases do not end in a punctuation mark, then the document is removed. Then it also removes documents containing any lorem ipsum, which in other words, it's just template text. It removes all the documents that talk about JavaScript or cookie notice. And then finally, we remove all the documents that contain curly braces. And just by doing that, the C4 dataset actually achieves great results. So what we did is we took these filters and we applied them to the FineWeb dataset. And we found out that this particular filter, the one that filtered out the documents with sentences that did not end in a punctuation mark, just that one just that filter actually ended up removing about 30% of our tokens, which we figured was too destructive. So what we did is we applied all of the other rules of the C4 dataset, but not that one, not the one that removed the documents without final punctuation mark. So what we did is we replaced that with our custom rules. And these custom rules are these three that you see right here. First of all, we remove documents where too few lines end with punctuation. So instead of removing every single line, we have a threshold of 12%. So when 12% of the lines do not end with a punctuation mark, then we remove the document. That also gives us a little bit more room to keep text that is actually well written, but sometimes does not end with a punctuation mark. We remove documents with many characters in duplicated lines, so the threshold was more than 10%, duplicated content across the documents. And also we remove documents dominated by very short lines. So if a document had more than 67% of the lines under 30 characters, we removed that document from the dataset. And after doing this, we removed 22% of the tokens instead of 30% that we would have removed if we had used just the C4 rules. And on top of that, we improved the benchmark performance, as you can see right here. So we have our baseline right here at the bottom, and all of the filters combined ended up performing much, much better. And when we compare this final version of the FineWeb dataset, you can see that it is much better than other open datasets online. And we actually ended up improving quite substantially over both FineWeb and C4. So we're already pretty well right here. And there you go. That is basically what we did to train the FineWeb dataset. Just to give you a very quick recap. First of all, we extracted 96 Common Crawl work snapshots and we cleaned them ourselves using Trafiladura. Then we just cleaned them using URL-based filtering, language filtering, and some very quick quality filters. We deduplicated within each crawl, not against the entire dataset. And then we added some C4 style and custom filters to remove more data. And we ended up with a 15 trillion token dataset that actually performs better than all of the other open datasets available at the time. Okay, so let's talk very quickly about the FineWeb-Edu dataset. And this is a very fun example of how you can use open models in the pipeline to improve on your existing data. And so why did we create FineWeb-Edu? First of all, Llama 3 and Phi 3 at the time reportedly using educational quality filtering. In other words, they took a huge data set and they filtered for only the documents that had the highest educational value. However, their classifiers were not public. So what we did is we trained our own classifier and we ended up getting much better results in this much smaller FineWeb-Edu, because remember that this one right here is just about above 1 trillion tokens, whereas FineWeb is 15 trillion tokens, and this one right here actually ends up getting better results in a bunch of educational heavy benchmarks. So let's take a look at how they did it. So the first thing that we did is we used a huge and very powerful model as an annotator. So we used Llama 370B Instruct, which is a huge model, and we used it to score about 500,000 FineWeb samples of 500,000 documents in our FineWeb dataset and score them from 0 to 5, depending on their educational value. So 0 would be 0 educational value, 5 would be something like PhD level educational value. And we, of course, asked the model to not just give us the score like that, but we gave it a bunch of very detailed rubrics that it had to argument on and had to score on, and then in the end, just add the whole thing to give us a score between 0 and 5. And that, of course, reduces hallucination to make sure that the model does not just hallucinate a random number between 0 and 5 for a given document. And we used this huge 70 billion parameter model to score all of these data points, but we would not have been able to just release this huge model onto a 15 trillion token dataset. So what we did is we labeled 1,500,000 data points with Llama 370B, and then we trained a smaller model on those already scored documents. And it was this smaller model that we used in then we released in the entire FineWeb dataset, and we got much better results by running a much smaller model. And in the end, we had a very well scored 15 trillion token dataset, and now we had to choose which threshold were we going to define to keep or remove documents from our data. And there were many different options we could have done. We could have removed anything below the score of 2, or anything below the score of 3, or anything below the score of 4. We ended up deciding on removing every document with a score lower than 3. And that gave us educational documents that were not only of university level, but also high school or secondary high school level right here, which is already pretty good, and it gave us about 1.3 trillion tokens. And when we tested this smaller 1.3 trillion token dataset against the other datasets that we have right here, so for example, we have FineWeb, we have FineWeb, we have C4 on educational benchmarks such as MMLU, we found out that FineWeb, with that tiny amount of data, actually ended up training much better models, as you can see right here. And to me, that is just crazy. And here you have the same FineWeb-Edu dataset, and it is compared against the FineWeb dataset that we just created, the refined web, the C4, and other open datasets online. And you can see that FineWeb-Edu actually ends up just destroying the other datasets and their aggregate score. So what are the main lessons for today? First of all, extraction quality matters. So we preferred using the raw format of the Common Crawl snapshots rather than the readily available wet text because it improved on the quality of our dataset. Also, that deduplication is not monotonic. You should not deduplicate the entire thing against itself, because a more aggressive deduplication can hurt your dataset. Evaluate with models, not only heuristics, so filters were selected via ablation runs, in other words. And evaluate with models, not only heuristics. What we did, as I mentioned a couple of times during the video, is that we trained the datasets on small models, and then we evaluated those models to see how good our dataset is. That is pretty much the best way to figure out if your dataset is good or not, because that is what these datasets are supposed to be used for, to train models. So by evaluating the models on those datasets, we effectively evaluate the datasets. And also something very interesting that we found out is that data quality varies over time, as I'm going to mention in just a moment, because we're going to see that later or more recent data snapshots are actually of different quality than older ones. And we're going to see a little bit more about that. And finally, that big large language models can bootstrap scalable filters. In other words, it is very possible to use a huge and very powerful large language model to label or to score a small section of your dataset, and then train a smaller model on that, which is the one that you're going to release onto your full dataset. And just for quick record, here you have the entire pipeline for both of these datasets. Remember that for FineWeb, we started with Common Crawl, then Work plus Traffiladura, the base filters of language and quality. Then we deduplicated, and finally we had the 15 trillion token dataset. And for the FineWeb-Edu, we started off with a FineWeb dataset. We labeled 1,500,000 samples from it with Llama 370B. We trained a small classifier on these samples right here. And then we selected for educational content with a threshold of 3 out of 5. So we ended up with a 1.3 trillion dataset when the threshold is 3 or more as a score, and which ended up getting much better results. And just before we leave, I wanted to give you a very quick bonus piece of information right here that is very fun and very nice to look at, which is the fact that Common Crawl snapshots actually vary in quality over time. And that is, I mean, pretty crazy in my opinion. So what's going on is that the quality of the data that we get from the web dictates how good our models are going to be, right? So that is why we did all of this filtering and all of this quality filtering, deduplication, and all of this education filtering, etc. So what happens right here is that just a very quick part of the experiment is that we took all of this extracts or snapshots from Common Crawl. I remember that we have one about every 1 or 2 months, and we train a small model on every single one of those snapshots. And we ended up finding out that the latest snapshots actually produce much better models. So recent DOMs are not just more data, they're often better data. And we started wondering about why that is the case. And as you can see right here, this increase in quality starts coming right here about 2022. And I don't know about you, but I can think of a very interesting thing that happened about this time right here in 2022. So we started wondering, would it be the case that the reason for this increase in quality is that we have more synthetic data on the web? In other words, we have more data generated by large language models. And turns out that most likely, yes. It is very difficult, of course, to predict or to classify a piece of text to figure out whether or not it was generated by a large language model. But we figured out a very quick proxy measurement to do this. We basically monitored some words and phrases that are very commonly used by large language models, such as delve into, certainly, and stuff like that. And we measured how often they appeared in our previous snapshots. And as you can see, before 2023, the frequency of those words remained relatively constant. And after 2023, we started with this explosion of those LLM signature words, which is, of course, not a proof that this is LLM generated data, but it does give us a pretty good hint that this might be generated by ChatGPT or a similar large language model. So this basically gives us a very interesting finding, which is that snapshots that have a lot of synthetic data end up producing better models. At least that is the case right now, where we have a tiny fraction of the snapshots being LLM generated data. Now, the question is, what is going to happen when the larger part of the snapshots is synthetic data generated by large language models? We'll have to figure it out as that happens. And by the end, let's just close this with just some open questions, which is, as I was telling you, will synthetic data make the web data worse? So right now we have a lot of synthetic data in the web, but not too much. Will having too much of this synthetic data harm the quality of large language models that we get in the future? And second thing that I want to mention is that this is, of course, a little bit of an older article that I'm presenting right here. So right now we have even better small models than the Llama 370B. So this is a 70 billion parameter model that was very good at the time, but we now have much better models that are sometimes below 20 billion parameters. So will the use of these smaller models allow us to create much more sophisticated data pipelines for classification and for synthetic data generation even? That is basically all for this presentation. Thank you very much. Of course, the slides for this are in the description. And if you have any questions, feel free to leave them as well in the comments. Thank you and have a great one.